What are we going to talk about? Like, okay, simple context pilot, whatever the project we have been working on, I can quickly show you GitHub context pilot. It's something that I've been working on and it requires a lot of, okay, I'm just gonna hit my name there. Oh, context pilot.newbim is more popular than context pilot itself. So over here, as you can see that this is the idea of the project and it does use a lot of asynchronous programming right now, and that's what my PR is all about. Okay. And given that I'm moving it from binary to server, that definitely means that it needs to be asynchronous because the server needs to run in the background. Now, the thing is, I can go and debug this for 10 streams from now onwards, or I can actually learn a bit more about asynchronous functions because honestly, like it's not a huge rocket science. The problem is, I think I'm missing the basics here. Um, and that's something that we should try to fix. And yeah, you should change your name from next time. It's all good. Dave. See, I remember your name. And for those people who are like just curious, they can go to Rust Code Project walkthrough. Can just go to my channel and try to look at this, and you will find my video there. And please feel free to subscribe to my channel if you can. Anyway, so we are going to go through this book in this set of streams, and I hope you guys like it. If any queries, you can put this in the chat or you can ask in the comments down below. So we all love how Rust empowers us to write fast, safe software, but how does asynchronous programming fit into this version? Okay, I'm going to skip this part, but that's very important. Asynchronous programming, or async for short, is a concurrent programming model supported by an increasing number of programming languages. It lets you run a large number of concurrent tasks on a small number of OS threads while preserving much of the look and feel of the ordinary synchronous programming. Yeah, I mean, I think this whole async or await syntax is just letting you write a keyword before you're defining mean, like whatever language you're using. For example, you can just put asynchronous and async, and that's it. This is very important. I wanted to kind of talk about it as well. I was asking ChatGPT last day that what is the difference between asynchronous programming versus multi-threading and all, right? So let's go through this. So concurrent programming is less mature and standardized than regular sequential programming. So sequential programming is what we generally do, right? We wait for the first instruction to finish and then we go to the next instruction. As a result, we express concurrency differently depending on which concurrent programming model the language is supporting. So there are a few concurrent models that they're going to talk about, right? So OS threads is one. These don't require any changes to the programming model, which makes it very easy to express concurrency. However, synchronizing between threads can be difficult and the performance overhead is large. This looks like just what we discussed. I believe that multi-threading and all, right? Basically just using thread. And I do believe that there's an advantage with multi-threading is that you do have shared memory within threads. So it's kind of faster to move around data within threads, but you also have a limit that how much data you can transfer within threads, if I'm not wrong. However, synchronizing between threads can be difficult and the performance overhead is large, right? That's also a thing because you're moving data within threads, and that's at least going to cost you extra, right? Instead of just doing it synchronous way. So it depends what you want to optimize on. Thread pools can mitigate some of those costs. As we discussed, I believe that's what they're talking about, but not enough to support massive IO bound workloads. That's like something we already talked about. Event-driven programming in conjunction with callbacks can be very performant, but tends to result in verbose. I'm going to skip this one. For those people who are coming from React and front end or something, they would know what is event-driven programming, but it's not relevant over here, I believe. Coroutines like threads don't require changes to the programming model, which makes them easy to use. Like async, they can also support a large number of tasks. However, they abstract away low-level details that are important for systems programming and custom runtime implementers. I think this just means that, okay, you don't have a lot of control on coroutines, probably, if I'm not wrong. Okay, and give me 1 second, guys. Let me make sure that I'm all right. Okay, what else is there? Coroutines is done the actor model. Okay, guys, you can see my screen, right? Okay, just confirming. Okay, all right. The actor model divides all concurrent computations into units called actors, which communicate through fallible message passing, much like in distributed systems. The actor model can be efficiently implemented, but leaves many practical. Okay. All right, I don't want to look much into this. In summary, asynchronous programming allows highly performant implementations that are suitable for low-level languages like Rust, while providing most of the ergonomic benefits of threads and coroutines. So it looks like, okay, they're just giving you everything that you want, but let's see what is missing, right? Yeah, this is very important as well, because not everything in async in Rust is equal to other languages. Do you actually know about coroutines? I have no idea how coroutines and threads are different and how it works internally. I just have heard about Go coroutines. I have not, like, honestly, um, even used them in the past, but what it looks like, maybe we can discuss that in one of the videos, and I can make a short video later on about this after I actually figure it out as well. But maybe once we go through this, or if you want, we can quickly ask. I generally do this. It's okay to ask, what's the difference between coroutines and threads? Explain with some tech details. 30 minute हो गए ये. Welcome, welcome Mohit, welcome bro, what's up? So coroutines and threads are both mechanisms used in programming for concurrent execution, but they operate quite differently in terms of implementation and usage. So OS perspective, threads are managed by the operating system kernel. Understand, each thread is typically associated with its own stack and registers. Switching between threads involves a context switch managed by the OS kernel, which is true because it's anyways managed by OS kernel, right? Threads can execute concurrently on multiple CPU cores if available. They are preemptively scheduled by the OS, which means the OS can interrupt one thread to allow the other to run. Threads share the same memory space, which we have talked about, shared memory and resources of the process they belong to. This shared memory requires synchronization mechanisms like locks, semaphores to ensure data integrity, which is something we'll take a look at later on. Threads are typically managed explicitly by the programmer using thread library or language constructs. Okay. Coroutines are implemented at the application level, not by the OS kernel. They are lightweight and can be multiplexed onto a small number of OS threads. Okay, so they are like, it's more like a feature in a language rather than a kernel itself. Concurrency coroutines are cooperative, meaning they voluntarily yield control to another coroutine. So you don't have really a lot of control on it. Does it mean that? I don't know. They do not concurrently by default. They do not run concurrently by default unless explicitly multiplexed onto multiple threads. So it just looks like coroutines is a just feature, or I don't know what you want to call it, but you can add this functionality, but it's not by default. Coroutines can have their own stack, but unlike threads, they typically share the same memory space and resources within a single thread of execution. So if you are running with like a single thread of execution with one coroutine, that's gonna share memory space and resources within that single thread. So if there's another thread that's running different, you can't really share, but within threads you can have a common space in memory and all. I'm sorry, I'll look at this. Yes, but it does not have the thread overhead of separate stack and stuff. Yeah. I mean, that's why I think, because it does have its own stack, but unlike threads, they typically share the same memory within a single thread of execution. So, like if you're doing concurrently, it might not be the best use case. Does that mean the same thing? Okay, this simplifies concurrency since you don't need explicit synchronization for shared data, which is what we talked about, like locks and all. Assuming coroutines are used in a single threaded manner or are synchronized by coroutine runtime. This is not we know, but overall this means that assuming coroutines are used in a single threaded manner, in that case it's easier to have shared data and all, because you don't need locks over here. That's that one. I mean, I hope they mean that. Coroutines are programmed using language specific constructs. Oh, so coroutines async await in Python, async await in C#, libraries boost coroutine in C++. I mean, that's why I think that's what you meant over here, that most of languages are there because it's like on the application level. So of course you can have third party control over there. Key differences is what? Threads are preemptively scheduled by the OS, which I understand. Async IO in Python is completely coroutines. Because I mean, there's no true multi-threading in Python as well, right? Until at least the CIL is removed, right? So makes sense for them to have a single threaded manner, which I think is very close to what coroutines are, right? Except the fact that threads are preemptively scheduled by the OS, while coroutines are cooperatively scheduled by the application code. Threads share the entire process memory space and require explicit synchronization, which is what we talked about. and the entire process memory as well, whereas coroutines can share resources within a single thread context, potentially reducing overhead and complexity. Hmm. Threads involve more overhead due to OS scheduling and memory isolation, whereas coroutines can be more lightweight. Threads involve more overhead due to OS scheduling, I understand, and memory isolation because you need shared memory given the process, whereas coroutines can be more lightweight and efficient for certain type of tasks, especially IO bound operations or event driven programming. Yes, but then Node.js does not use coroutines, yet being single threaded is what I don't understand. I mean, depends what you mean by coroutines. Like coroutine, they would have had something, just they have not named it coroutines. It could be that, right? Okay, wait, Node.js. Wait, I can ask the ChatGPT. One thing I'm just going to finish. The threads are used for tasks requiring parallelism or multi-core systems, or when you need preemptive multitasking with separate stacks and full memory isolation. Coroutines are ideal for asynchronous programming, event loops, and tasks where many concurrent but not necessarily parallel operations are involved. Okay, wait. I have to ask. Uh, the Hyperlink setup looks good. Hi, Bhavan. Thank you so much for joining us. What's up? And yes, it took a lot of time. If you were on my Discord, you would have seen it was a huge struggle. I was always, I mean, almost given up. But yeah, given that it's single threaded. Let's see, Dave, to your question. Node.js does not use coroutine. Oh, but I've got to leave. It's okay. It's okay, Bhavan. Thank you so much for joining us. Take care. Bye bye. Node.js does not use coroutines in the traditional sense, but it does use an asynchronous event-driven programming model that achieves similar benefits to coroutines in terms of managing concurrently. Okay, event loop and all, non-blocking I/O, callbacks and promises, concurrency model. What's the difference though? Coroutines typically involve cooperative multitasking where control is explicitly yielded between tasks. In contrast, Node.js uses an event loop where tasks are executed asynchronously and are scheduled based on I/O events. I don't understand this, by the way. What is cooperative multitask scheduling and all? I should research a bit more about it. Memory and resource management. Node.js applications share the same memory space and resources within the event loop. Hmm. All right. Okay, you can look at this honestly, but benefits overall, they say that Node.js can handle many concurrent connections efficiently without the overhead of threads or coroutines. Due to its non-blocking IO model and event-driven architecture, Node.js is well suited. I do think that coroutines are also non-blocking IO model, right? Like it's only single-threaded, so there will be no blocking as such. Yeah, I know, right? It just said coroutines are used in event loop. In the above thread, now it says Node.js uses event loop. It could be that Node.js have made a design choice. Let's see. Maybe they would have JS coroutines and all, of course, are there. Okay, I think there are some questions around it. I don't know enough about Node.js, I'll be honest. So I have no idea. But I can probably we can take a look at this later on. They do have on GitHub JS coroutines. The last commit was 3 years ago. All right, if you don't mind, let's carry on, and I will maybe we can take a look at it later on. So async in Rust versus other languages. All the asynchronous programming is supported in many languages. Some details vary across implementations. So futures are inert in Rust and make progress only when polled. Dropping a future stops it from making further progress. What does that mean? It's a design choice, of course, but was it? It was with a reason. I guess Python already had event-driven programming in coroutines even before Node.js. It was so popular. I think I do remember Go following the coroutine culture very nicely, and that would have got it the popularity. I don't know about how Node.js. When did they start? What kind of design choice? I mean, what was the reason behind it? So yeah, I don't understand this part, by the way. Futures are inert in Rust. In Rust, futures are fundamental concept of for representing asynchronous computations. I do understand what is a future, They encapsulate an operation that may complete in the future, allowing the rest of your program to continue. A feature in Rust is a type that represents an asynchronous computation. Yes, Go coroutines. This is, I don't know why Google came up with this and then they don't realize it's actually hiding the text. Coroutines are called coroutines, it's their own thing. Oh. A feature in Rust is a type that represents an asynchronous computation. It holds the logic for an operation that is expected to complete with a result at some point in time in the future. Yes. Features in Rust are inert or lazy, meaning they do not execute automatically when created. Yep, I understand. Instead, they start executing only when they are actively polled by calling the poll method. Okay. Polling, the primary method associates with the features is poll. This method checks whether the feature is completed or if it is ready to make progress towards the completion. When you call poll on a feature, it returns poll pending if the feature is not ready to produce a value yet. Interesting. When would this be the case? It could be that the feature has not received the required data and that's why it is pending, but I'm very curious when will it return pending. And then is poll ready result if the feature is completed with the result. Or pending could be just ongoing, I guess, right? I would also want to know that if there's a way for us to know that if poll is not really ready to even find out if it's pending or not. What else is there? Progression by polling. Polling mechanism, future makes progress only when you explicitly poll them. Okay, all right. Dropping a future. Yeah, okay, what is it? Each time you call poll on a future, it may perform some work towards completion, initiating an IO operation, etc. If the future is not ready to produce a result immediately, it returns poll pending, like example, waiting for IO or a timer. Okay. In that case, like, okay, IO is on the hardware side if it's not ready yet. Okay. Okay. Continued polling. The consumer of the future typically continues to poll it until it returns poll ready, indicating that the operation has completed successfully or with an error. Okay. Yeah. And that makes sense. That's okay. Dropping a future, cancellation in Rust, dropping a future typically means stopping further interaction with it. When a feature is dropped, any associated resources or tasks that were part of its execution may be cleaned up. That's interesting though. Okay, they have a really, really nice example. Impact on progress, dropping a feature does not explicitly stop it from making progress unless there are specific cleanup actions associated with dropping. Does not explicitly stop it from making progress unless there are specific cleanup actions associated with dropping. Okay, wow. So if it's already running, it will not stop. It's just stopping further interaction with it. If a feature is dropped before it completes naturally, it may not complete at all, depending on its implementation and the resources it manages. Yep. Some features may have cleanup logic in their drop implementation to handle this scenario gracefully. This is what they mention over here, I guess. Simple future for me, my future, you have is ready bool, function poll. Okay. Is ready, poll ready 42. 40 is the universal truth. Get mute is ready equal to true. Wake up, wake by reference. Notify the executor to poll again later. Oh, nice. And then you have my future is ready false. Context from waker. Poll the future until it completes. Nope waker. Okay, this is what you're calling this. I don't know what this means, to be honest. Okay. Oh, there you go, right. Okay. Nope waker impulse to task, whatever, function wake. Alright, that's a lot to digest. Okay, for now. This is okay. We can go ahead. Async is zero cost in Rust, which means that you only pay for what you use. Specifically, you can use async without heap allocations and dynamic dispatch. Okay, which is great for performance. You can use stack for async. Okay, without heap allocations and dynamics dispatch. This also lets you use async in constrained environments such as embedded systems. Alright, and then you have no built-in runtime is provided by Rust. Instead, runtimes are provided by community maintained crates. No built-in runtime is provided by Rust. Okay. So runtimes are provided by community maintained crates. Okay. Both single and multi-threaded runtimes are available in Rust, which have different strengths and weaknesses. All right, that's okay. Yeah, this is something I want to focus on. Async versus threads in Rust. The primary alternative to async in Rust is using OS threads, either directly through stored thread or indirectly through a thread pool. Migrating from threads to async or vice versa typically requires major refactoring work, both in terms of implementation, any exposed public. Okay, as such, picking the model that suits your needs early can save a lot of development time. Okay. OS threads are suitable for small number of tasks since threads come with CPU and memory overhead. That's true. Spawning and switching between threads is quite expensive because there's context switch, as even idle threads consume system resources. It's interesting. I mean, resources can also mean memory and storage, by the way. So that makes sense because you have memory allocated to each thread, right? Even if it's idle, it has memory. A thread pool library can help mitigate some of those costs, but not all. However, because if you have a library on the top of it, maybe they will monitor idle threads as well and let go of those resources. I don't know. However, threads let you reuse existing synchronous code without significant code changes. No particular programming model is required. In some operating systems, you can also change the priority of a thread, which is useful for drivers and other latency sensitive applications. Interesting. Asynchronous provides significantly reduced CPU and memory overhead. Hmm. So if a large amount of overhead IO bound tasks, in that case, yeah, switching context switch will be a lot in threads, right? So in that case, yes, it makes sense. All else equal, you can have orders of magnitude more tasks than OS threads because an asynchronous runtime uses a small amount of but expensive threads to handle large amount of tasks. However, async rust results in large binary blobs due to state machines generated from async functions, and since each executive bundles in async runtime. What do you mean by that? However, async rust results in larger binary blobs due to the state machine generated from async functions. Okay, I see, I see. So async function do generate the state machines that are saved in those binary blobs. And since each executable bundles an asynchronous runtime, so with each executable, you do get an asynchronous runtime, which you would need if you're having an asynchronous model, right? On a last note, asynchronous programming is not better than threads, but different. If you don't need asynchronous for performance reasons, threads can often be simpler alternative. In this example, our goal is to download two web pages concurrently. In a typical threaded application, we need to spawn threads to achieve concurrency. Okay. So you have thread spawn, you are threading one thread which is downloading food.com, the other is downloading bar.com. Then you're waiting for those threads to complete. And yeah, that's when you're ending the program. So it's like downloading a web page is small task. So if you're creating a web, like a thread for this amount of work is quite wasteful. For a larger application, it can easily become a bottleneck. In asynchronous Rust, we can run these tasks concurrently without extra threads. So you have asynchronous function over here. Create two different futures. So this is overall returning a future to you, which when run to completion will asynchronously download the web page. This is also download async, right? Okay, this is different. So this also needs to be a download and this should return a future now. So now we are saying run both future to completion at the same time. So this is like concurrent as well. And you are kind of waiting for them to complete. No extra threads are created. Additionally, all function calls are statically dispatched. Okay, and there are no heap allocations. However, we need to write the code to be asynchronous in the first place, which is what will help you out, which is what the book is for. All right, okay. So far, so good. All right, okay. Let's go and look at this. Parts of async Rust are supported with the same stability guarantees as synchronous Rust. Other parts are still maturing and will change over time. With asynchronous, you can expect outstanding runtime performance for typical concurrent workloads. Okay, guys, I'm going to stop here. I think this will be too much for us to digest as well, given that we had a bit of context switch. But okay, maybe in the next stream we can go around it. I need to hop off, but yeah, thanks for sticking around. I don't know how many people are here, but if you're watching this video as well later on, thank you so much for watching. And I am reading it in front of you, so please don't consider me an expert. I'm nowhere near to an expert, but I'm hoping that I'll be there one day and I'll make my own videos without reading books. I don't think that's gonna happen, but yeah. Thank you so much, everyone. That's it.